speak at the seminar. Thank you for this opportunity, and thank you to everyone who made the time to come to my talk. So I will talk about a cohomology theory that we can attach to modular forms called Eichler cohomology, and in particular about a class of objects called period polynomials that we can use to compute these cohomology groups. I'll start with some historical motivation that's coming from Eichler integrals for studying period polynomials. And then we'll get into the definition of Eichler cohomology. I'll be very explicit of how we construct it, some of its properties. And then after that, we'll actually see period polynomials coming from this Eichler cohomology theory. Lastly, I will talk about some properties of these period polynomials. We'll look at some of their analytic properties, in particular, the location of their zeros. At the end, I'll touch upon a project that we did last year with Larry Rolen and Ian Wagner at Vanderbilt University, where we attached period polynomials to Hilbert modular forms and proved that at least when the level is full, the location of their zeros is on the unit circle. All right, so let's look at some motivation, and we'll start with some notation. We'll take gamma to be a finite index subgroup in SL2Z. K will be an even integer greater than or equal to 2. We have the C vector space of weight K modular forms on gamma with coefficients in C. And then we also have the subspace of weight K cusp forms. All right, so I suppose I will use the /K operator a couple of times in this talk. So when we talk about a modular form, we mean a holomorphic modular form from the upper half plane into C. So it's holomorphic. And it satisfies a bunch of different properties, which you've probably seen about modular forms, but I want to talk a little bit about the /K operator, in particular for gamma, for little gamma in our subgroup gamma. The slash operator with K of Z gives us the following expression. We get CZ plus D to the minus K f of gamma dot C, where gamma is the matrix ABCD, and then the action on Z is just a Mobius transformation. AZ plus B over CZ plus D. So for F to be a modular form implies that F/K is equal to F. All right. If we have two modular forms of any weight, their product is still a modular form, and therefore we can create a graded ring if we put all of the different weights together. In particular, if we take gamma to be a subgroup in SL2Z, we will actually have K being greater than 0, really. And then it's a fact that it's fairly known that the graded ring for SL2Z with coefficients in C is generated by the Eisenstein series E4 and E6. Another object that I will use is a graded ring of what are called weakly holomorphic modular forms. The weakly part allows for poles at cusps. So in particular, this allows the weight K to be negative. Oops, won't really, all right, here we go, negative. The context where we'll use this graded ring is when we're talking about some differential operators. All right, so let's look at the following differential operator D. I will think of f of z in terms of its Fourier expansion. So we have an q to the n, where q is e to the 2 pi I z. Then the differential operator df, or sometimes it's also written as f prime because it's really just the derivative of f with respect to z, except that we're extracting a 1 over 2 pi I in front. In terms of the Fourier expansion, we get that this is equal to q df over dq, or we take the nth power in front of the Fourier coefficient. Now, the interesting part is that D does not act on the graded ring of holomorphic modular forms. So it does not act on that M of gamma. And we might want to check why that is so. So let's take a matrix ABCD in gamma, and then let's look at what is df of gamma dot z. Well, the first part is fairly standard, and it might give us some reason for optimism. So we get a cz plus d to the k plus 2 df of z. And then if we see this, we're thinking, okay, this kind of looks like a modular form, maybe a weight k plus 2, but we also have an extra term given by k over 2 pi I times c, cz plus d to the k plus 1, f of z. So this entire part is an extra term. In particular, df is not a modular form because of the existence of that extra term. However, we might be able to get around it if we subtract the contribution of what gives that extra term. So df is not a modular form, but if we subtract k over 12 times E2 times f, where E2 is the weight 2 Eisenstein series, we do get a modular form of weight k plus 2. So in fact, the fact that D does not act on M of gamma doesn't prove to be a bug, it's more like a feature. So it gives us some extra richness. All right, one example that I really like to think about occasionally is that D acts on the following algebra, generated by E2, E4, and E6. In particular, okay, sorry, I have to move something. All right, E2 prime is equal to E2 squared minus E4 over, I think, 12. E4 prime is E2 E4 minus E6 over 3. And then E6 prime is E2 E6 minus E4 squared over 2. So that's pretty neat. All right, so we have this differential operator. The next step is going to be the definition of these Eichler integrals that I briefly mentioned at the beginning of the talk. In particular,
ask a question.
Yeah.
The previous algebra is called like quasi-modular forms, right?
I believe that is correct. I honestly have all of my terms occasionally backwards, so I think you're right. E2 is definitely a quasi-modular form, but I honestly don't remember exactly the definition of a quasi-modular form, but I believe you're right.
Okay, thanks.
Yeah, great observation. Any other questions about this example? All right, if there are none, I'll move on, but I will leave some time after each of my subsections for questions. All right, so in particular, we have that D will act on that graded ring of weakly homomorphic modular forms. And if we apply it k-1 times, we get a map from the weakly holomorphic modular forms of weight 2 minus k into the weight k weakly holomorphic modular forms. So we have a differential operator, and we might want to ask, okay, well, what happens if we're taking the inverse of this operator? And that's exactly where the Eichler integrals are coming from. We might want to look at what is the inverse image of a cusp form. So the Eichler integrals are really just formal k-1st antiderivatives of cusp forms. In particular, if we take f of z a cusp form, and it has a Fourier expansion, we can get one antiderivative as follows. We have the coefficients an, n to the 1 minus k, q to the n. So that's one antiderivative. And we might want to ask, okay, what properties does this uppercase f of z, does this antiderivative satisfy? Well, it makes no sense for us to expect it to be a modular form. However, we might expect it to act nicely with respect to that slash operator. So what we can do is that we can compute, for example, the following expression. So I'm going to write something that's not technically true, but okay, we apply d k-1 times to f, where we take the slash 2 minus k of 1 minus s. And what I really mean by this is not really we take the slash of 2 minus k of 1 minus s, but it's really we first take the slash with respect to the identity, and then we subtract the slash action with respect to s. Okay, I just want to condense a lot of my notation. Here, we get that this equals 0, where s is this matrix that we all know and love. All right, so we have the derivative, the k-1st derivative of a function is 0. Well, that means that that function isn't really that sophisticated. It's really a polynomial. In particular, this function is a polynomial of degree at most k-2. This is what we will call a period polynomial. All right, so we see why it's a polynomial. I'm not really elucidating the meaning for like the period part, but I will do after we talk about Eichler homology. We'll see these period polynomials being defined from a different perspective. And these period polynomials have quite a few different applications. I'll just mention some of the earlier applications by Shimura in 59. Who got some applications to elliptic curves. And there's also an application by Manin in 79 to critical values of L functions. And we'll actually see this result a little bit later in one of our examples. Okay, and we associate these L functions to cusp forms. All right, before I move on to Eichler homology, are there any questions? All right, let's move to the next section. Eichler-Chromology. We will consider the following space. We take vk minus 2 to be the complex polynomials of degree at most k minus 2. All right, and this space lives in C of x. We also have a slash action of gamma on this space. So gamma acts on V of k minus 2 if we have a matrix A, B, C, D. Then the action of gamma, and I'm not actually going to write k minus 2 or k on the bottom because in this case, the weight is really fixed. All right, so this action is equal to Cx plus D to the k minus 2, P of gamma dot x, where gamma dot x is the Mobius transformation. I also define a related object, a related module, which I call vk minus 2 with a tilde, to be the set of maps from SL2Z modulo gamma, so from the left cosets into V sub k minus 2. All right, so we get a tuple of complex polynomials. And we get exactly the index of gamma in SL2Z, many complex polynomials in each tuple. Okay, we also have an action of SL2Z now on this vk minus 2 tilde. In particular, we act by gamma on R, and the value of this new tuple at A, remember this is a coset, equals R of A gamma inverse slash gamma, where this slash action is the one that we introduced right here. So we have two different modules. One of them is a gamma module, one of them is an SL2Z module, so we can look at cohomology groups from the action of the group. Or in particular, we can look at group cohomology. So we can look at either this group cohomology with coefficients in ek minus 2 tilde, or this group cohomology with coefficients in v sub k minus 2. From Shapiro's lemma, these two will be equal, but we'll get to that in a little bit. All right, I will do a very quick refresher of group cohomology. So if we take G to be a group and M a G module, we can define some abelian groups, Cn of Gm, to be the maps from n copies of G into M. I should say that G0 is just the identity. So in particular, C0 is just isomorphic to the module M. And if we have all of these abelian groups, we can make a cochain complex. 0 into C0 into C1 into C2 and so forth, where we have these co-boundary maps, D1, D2, D3, and so forth, where each of these co-boundary maps is defined as we see here. The exact definition won't really factor in my talk, but the important part of these cochain complexes and these co-boundary maps is that the composition of any two consecutive ones gives us 0. Equivalently, that means that the image of D n is contained into the kernel of Dn plus 1. We say that the sequence is exact if the image always equals the kernel. If it's not, we might want to see how far the sequence is from being exact. So we can define the following submodules. So the n cocycles Zn of Gm to be the kernel of the Dn plus 1 map, and the n co-boundaries denoted by B n of Gm to be the image of Dn. Then the nth cohomology group is cocycles modulo coboundaries. Okay, so if cocycles equals coboundaries, we have exactness. Otherwise, we have some interesting groups, these cohomology groups. All right, so let's go back to those objects that I defined before, those modules, and see what sort of cohomology groups we get in that case. So technically, I will actually want to not really work with vk minus 2 tilde. I will want to refine it a little bit further. And the reason why I want to do that is that there's no reason for us to expect for the those abelian groups Cn that I defined to be full of just cocycles. So we might want to restrict our those abelian groups Cn to contain what are more likely to be cocycles. Okay, so we'll see what that means. From Shapiro's lemma, we can say that the two cohomology groups H1 of gamma with coefficients in vk minus 2 is equal to H1 of SL2Z with coefficients in vk minus 2 tilde. All right, Shapiro's lemma really just identifies cohomology groups of induced modules. All right, and let's take sigma to be a cocycle, right? So a map from SL2Z into vk minus 2 tilde. What does it mean for it to be a cocycle? The cocycle condition says that if we take sigma of gamma 1, gamma 2, we really get sigma of gamma 1 plus sigma of gamma 2, and then we slash with gamma 1. Now let's take a one coboundary. What does it mean? Well, it means that we have a map in vk minus 2 tilde such that tau of gamma equals r slash gamma minus r. All right, the next step that I want to do is see, okay, so if we have a cocycle, what sort of conditions, besides just the cocycle condition, can we impose on it based on the slash action from the different elements that we know exist in our group? In particular, let's take J to be minus the identity. Then the fact that sigma is a cocycle, as well as the fact that J will commute with anything in gamma, will imply the following equality. So it might just look like symbol soup for now, so maybe you can take a few seconds looking at it and see if anything occurs to you. Okay, maybe something did occur to you, maybe it didn't. So here's a hint. Is there anything special about this part? Well, it is a coboundary. Based on that condition that we just wrote here. That means that the left-hand side and the right-hand side here really just differ by one coboundary. So that means that they are the same in the cohomology group. They have the same cohomology class. Okay, so if we have sigma, a one cocycle, we also need the following equality to hold. Now, in terms of polynomials, we get that r/j of a equals r minus a. If we have a map R equal to sigma of G, where G is a coset. Okay, and based on this condition, I will define the following submodule. Vk minus 2, and then I will put a gamma up top. We will take the elements in Vk minus 2 tilde such that R of A equals R of minus A. So this really gives, in a sense, a symmetry relation between the value of R at different elements in the coset, at the different cosets. We really didn't do much by restricting Vk minus 2 tilde to Vk minus 2 gamma. In particular, the cohomology groups, whether we take coefficients in Vk minus 2 tilde or Vk minus 2 gamma, doesn't change the cohomology. Okay, one last restriction, I promise. I will want to restrict further to parabolic homology. And parabolic homology really looks at what happens at the cusps, okay? In particular, it is the kernel of a restriction map. So the map itself goes from H1 of gamma, Vk minus 2, gamma into a product over cusps. Okay, so equivalence classes of cusps of H1, and then I write gamma C for the stabilizer of the cusp with coefficients in Vk minus 2. And I'm actually not sure if this should be a gamma or not. Okay, I'm not sure if this should be a gamma or not, so I'm going to put a question mark. Okay, so this gamma sub C is a stabilizer. At the cusp. Okay, so this is the restriction map, and then the parabolic homology group is going to be the kernel. So as an example, if we have gamma to be SL to Z, we'll have one cusp, infinity. The stabilizer at infinity is generated by this translation matrix. So sigma in the parabolic homology group implies that sigma of any power of t should be 0. Okay, we will see why this condition makes sense in just a little bit. Okay, before I introduce period polynomials, I want to give some more context into where these cohomology theories, such as Eichler cohomology, have been used. For one, Knop defined these rational period functions, which we can call RPFs. And we can basically extend Eichler cohomology to weights less than 0. Then the coefficient module will consist of these rational period functions. These rational period functions came from not necessarily those Eichler integrals that we talked a little bit about at the beginning, but to more generalized automorphic integrals. Okay, and these rational period functions then satisfy some conditions, Ash then gave a full description of these rational period functions with whatever properties they satisfy via cohomology. However, that explanation was very abstract. For something more explicit, Choi and Zagier gave a description in 93 in terms of Heck operators. More recently, in the rigid analytic setting, German and Bong have introduced these rigid meromorphic cocycles, although I'm sure there's a lot more other interesting cohomology theories that are related to Eichler cohomology. Okay, I think this might be a good time to take a 2-minute break, and if anyone has questions, let me know. Yeah, we'll take a little break if anyone needs to get up, get a tea. So I'm actually curious, Jerome, this is probably where it would have been the right time to mention what you were talking about, but
well, when K is positive, these things have a clear description in terms of cohomology. And it's exactly what I was telling you about, is that you look at the fibers. So if you're looking at the modular curve, you take the upper half plane mod gamma, and you have you have a fiber space of elliptic curves over that thing, and you take powers of that elliptic fibration. So you get E squared, E cubed, and so on. And you get a bunch of, these are called Kuga varieties. And basically, at least when K is positive, the Eichler cohomology can be interpreted as a part of the cohomology of the Kuga fiber spaces. Okay, it's a little complicated to say it, but that's the way to say it. But I don't know what happens when K is negative. This is something I'm not quite sure of. You mentioned Ash. Now that's interesting because I'm not sure what, I guess that's Abner Ash.
Yeah.
So I'm not sure what kind of description he gave when K is negative. So this is something that's new to me. So I'm not sure what happens when you take, I mean, it doesn't make sense to take negative powers of an elliptic curve. So, I mean, that kind of description doesn't make sense. But it might have a description in geometry in terms of some kind of cohomology of a fiber space, but I can't even tell you what it is now, just looking at it.
Yeah.
To a geometer like me, I mean, I understand Eichler cohomology in terms of these Kuga fibrations. And indeed, you can replace gamma by a quaternion group. It's like Fang-Ting and I are looking at, and you get, but what happens now is you don't have elliptic curves anymore. You have higher dimensional abelian varieties as your fiber spaces.
Well, you can probably still take products of that, right?
Oh, absolutely. These are Kuga fiber space. These are Kuga fiber space. Shimura and Kuga studied these back in the 60s. Absolutely. And Fang-Ting and I are, secretly at work on some of this. When, at least in the quaternion case. And of course, what you're saying is relevant to that. But you don't have cusps. See, the one big difference when you don't have, in the quaternion case, you don't have cusps, but so what? I mean, you can still talk about, the cohomology groups, it's still meaningful.
From what I recall from Ash's paper, the K less than 0 and K greater than 0 was really different. So very different things happened, but
I'm going to have to take you piqued my interest, so I'm going to have to look up this paper and see what they do. But anyway.
Okay. Well, thanks for the comment.
Sure.
Okay, so I guess our break is over. So let's talk about period polynomials, and I'll give a definition of period polynomials now in the context of Eichler cohomology. So let's take F to be a weight K cusp form. We can associate to it a map from SL to Z into Vk minus 2 gamma, right? In particular, this is how we're going to define it. It's going to be the following integral. All right, A here is going to be a coset. So, okay, technically, right, sorry, this should be modulo gamma, right? And then maybe you will be a little bit concerned about this. Well, what if we take a different coset? Turns out we don't have to worry. The choice is independent of the coset because F is taken to be a modular form. So this is independent of choice of coset because F being a modular form tells us that. So this slash action gives us F. All right, so here's some facts that I'm not going to get too much into. Sigma of F is indeed a one cocycle. Okay, it satisfies the cocycle condition. 2, well, SL to Z is generated by the two matrices S and T. So we can kind of, if we know how the value of sigma of F at S and T, that should tell us, hopefully, the value at all the elements of SL to Z. In particular, just from the definition, we see that sigma F of T to the N is 0, right? Because T stabilizes the infinity cusp, all right? In particular, it is going to be, we get a cocycle in parabolic homology, the way we discussed a couple of slides ago. On the other hand, so we know that sigma of F of any power of T gives us 0, so really it's sigma of F is just determined by the value at S. So the value at S is the following integral. We get the 0 from taking S inverse of I infinity, and we call this R sub F, which is going to be our period polynomial associated to F. Okay, then a third fact is that if we look at the definition, we see that sigma of F of S squared is 0, so is sigma F of U cubed, and so is sigma F of U times S, where U is equal to T times S. All right, then the cocycle condition will give us the following, that RF slash 1 plus S is 0, and so is RF slash 1 plus U squared, also equals to 0. Okay, again, this sum is really just an abuse of notation, right? We just take the slash over each of them separately and then we sum. All right, from here, we can define the following subspace of Vk minus 2 gamma. We will take those elements, those maps that satisfy the following conditions. On the one hand, if we slash with 1 plus S, we get 0. On the other hand, we slash with 1 plus U squared, and we get 0. And if we slash with J, we get R. This is what we call the space of period polynomials. And in particular, they're all one cocycles in parabolic homology. Okay, what about coboundaries? The one coboundaries are defined the following way. We take an R and we slash with 1 minus S, where R now has to be in K minus 2 gamma, and also R slash T equals to R. these are one coboundaries. A fun fact is that the dimension, maybe I'll write it here, the dimension of ck minus 2 gamma equals the dimension of the Eisenstein subspace. Okay, so in particular, the parabolic homology, the first parabolic homology of SL2Z with coefficients in Vk minus 2 gamma is isomorphic to, well, cocycles modulo coboundaries. All right, I want to get back to the connection between parabolic homology and modular forms. The connection is given by the Eichler-Shimura isomorphism. So let's take gamma to be just SL2Z from now on. It will just reduce some of my notation, although the Eichler-Shimura isomorphism works in other cases as well. Then we had a bunch of reductions, right? We had V sub k minus 2, then we had V sub k minus 2 tilde, then we had V sub k minus 2 gamma. In any case, when gamma is SL2Z, V sub k minus 2 gamma is just the polynomials of degree at most k minus 2. It really simplifies the situation a lot. We can actually compute what the one coboundaries are, okay? So if we go back up to the definition, okay, we have that R slash T of x has to be equal to R of x. Well, this is just R of x plus 1. So the question is, what polynomials are periodic with period 1? Well, it's just constant functions. So from the definition, we can get that the one coboundaries are given by the following functions. We have c times x to the k minus 2 minus 1, where c is a constant in C, and indeed it's one-dimensional. We know that the Eisenstein subspace for SL2Z is always one-dimensional for each weight. We just have one Eisenstein series. Okay, that was a bit of a detour. I like working out this example in particular. But to get to the Eichler-Shimura isomorphism, we need one more ingredient. Let's take the matrix minus 1, 0, 0, 1. Then the slash action on R, in this case, R is just a polynomial of degree at most k minus 2, equals just R minus x. In particular, the action of epsilon will split all of the different subspaces into plus minus eigenspaces. On the period polynomial, on the polynomial side, we can also split any polynomial into its even part and odd part. So R plus of x is just the even part, where we just take the terms with an even power, and R minus x is going to be the odd part. Then the Eichler-Shimura isomorphism states the following. If we take the map R plus minus from the cusp space, in this case it's SL2Z, but we can really just do it for any subgroup gamma, well, we get a polynomial that's either even or odd, whether we take R plus or R minus, right? So we take first modular form, then we get a period polynomial, and then we split it into its even or odd part. This map induces an isomorphism. Between sk of gamma and the following. So we have wk minus 2 gamma plus minus over c k minus 2 gamma plus minus. So really, in a way, we have identified the cusp space with those parabolic cohomology groups. It's kind of like the parabolic homology group is really kind of like twice the cusp form space. I want to take a minute to make an observation about this isomorphism. It's not just an isomorphism of vector spaces, okay? That would just tell us about dimensions. It's more than that. We can also define Hecke operators on these period polynomials. I don't really have time to do that, but they do exist. And this isomorphism also preserves the Hecke operator. In a way, it's also an isomorphism of Hecke modules. That's very important because I assume there's a lot of computational number theorists in the audience, and you know that if you're trying to get a modular form in like Sage or Magma or wherever, you're probably doing it like in the background, it's from modular symbols, right? And modular symbols work exactly because of the Eichler-Shimura isomorphism. In a way, in fact, period polynomials are dual to modular symbols, and they could also be used to get spaces of modular forms. Okay, so with that aside, let's talk about some examples of actually computing some period polynomials. Let's take F to be a cusp form of weight K with the following Fourier expansion. It has a L series associated to it. To the L series, we have a completed L function lambda, which we can also see in the form of the following integral. Then Rf of x, in this case, it's going to be equal to the following integral. But okay, this entire part, right, if we raise it to the k minus 2th power, we can separate it into the different x to the n terms, and then we'll see that each of the coefficients for each x to the n is basically given by critical L values. Right, and this is where the period part comes in, right, because we have an integral from like 0 to infinity of the value of the function and so forth. All right, a more specific example, let's take delta, our favorite modular form. Well, I don't know about yours, it's definitely my favorite modular form. Then the period polynomial is going to be approximately the following. Okay, I say approximately because these two things are transcendental. However, once we take out the transcendental part both from the even and the odd part, we get rational polynomials. So the odd part is basically rational and the even part is basically rational. Okay, so that's one property of these period polynomials. That's pretty cool. The other one is, if we're going to look at this polynomial, we'll notice that its roots lie on the unit circle. And that's a more widespread phenomenon. Conry, Mamoglu, and Farmer proved in 2013 that if you just take the odd part, okay, so just the odd part of period polynomials, their roots lie on the unit circle. For the, actually, that doesn't hold for the even part. The even part doesn't necessarily have roots on the unit circle. However, if you take both the odd and the even and you get the full polynomial, it does hold true when gamma is equal to SL to Z. The roots are on the unit circle. Jean Mallon and Sandarajan extended that for when gamma is equal to gamma naught of n. So then the roots don't lie on the unit circle, but they lie on a circle centered at the origin. And we also extended with Larry Rolen and Ian Wagner to Hilbert modular forms of full level, and we proved that the roots also lie on the unit circle in that case. Okay, as my last slide, I want to just do some observations about our proofs. And in general, all the proofs that I've seen about the location of the zeros really rely on analytic methods and computer checks. So they use the fact that polynomials are self-inversive. There are so many different definitions of self-inversive that I don't really want to get in. For us, in our paper, it basically had that Rf of x is equal to a root of unity times x to the k minus 2 over 2 times Rf of I to some power times 1 over x. So right, this is where the self-inversive part is coming in. In particular, if you have a root that's outside the unit circle, if you have one, then its mirror image should be inside the unit circle. In particular, if you're starting with a root that's already on the unit circle, its mirror should also be on the unit circle. Okay. Another observation is that in the Hilbert modular form case, we extended the definition of the period polynomial in a natural way, in the sense that the coefficients are also given by critical values of the L function. But it's not clear how our definition is natural in the sense of cohomology. So in particular, all of the proofs that we've seen tell us that yes, the roots are on the unit circle, but they don't really tell us why. And it would be interesting to see if any of the information from the cohomology can tell us why the roots are on the unit circle from maybe a more algebraic standpoint. I've actually seen a paper published recently by Yeonju Choi, where she referenced that she was working on a preprint to extend some of the cohomology theory to period polynomials for Hilbert modular forms. And I'm very curious about that, but for me, at least, that's not very clear at all. Okay, and I believe this is where I end. So thank you so much for your time, and let me know if you have any questions.
Any questions?
Just one comment. I mean, looking at your integral for Hilbert modular, of course, a Hilbert modular form is on a product of upper half planes.
Mm-hmm.
And in effect, you're doing a kind of cuspidal integral there.
Mm-hmm.
So it looks vaguely like the shape of such a thing, but of course, the geometry is much more complicated. I mean, you're no longer, I mean, there are cusps, there's the concept of cusps, but you're taking a product of upper half planes modulo a Hilbert modular group. It's going to be a Hilbert modular variety. It won't be it won't be a modular curve anymore.
Mm-hmm.
And I'm pretty sure that some of these fancy French guys have defined, for Hilbert modular forms, these cohomology groups that extend this. I'm trying to remember the names of some of these people, but of course it's all done in very fancy language using étale cohomology and all this other stuff.
Mm-hmm.
But of course, they're not trying to get anywhere near explicit calculations. Yeah, so I'm trying to remember the name of that French guy who wrote a thesis, I think, on. See, they're sometimes called Hilbert Blumenthal. Well, in fact, sometimes they limit themselves to just Hilbert modular surfaces, product of two.
Mm-hmm. Mm-hmm.
They're sometimes called Hilbert Blumenthal surfaces, and but I would bet you that one of those guys has considered this theory from that point of view. I mean, again, I can tell you how this story would go. I mean, so these Hilbert modular varieties, they're also moduli spaces, okay?
Right.
And they parametrize abelian varieties with real multiplication structures, okay? They're what are called PEL type Shimura varieties. And they have fiber spaces as well, just like the case of, the classical modular. So, the story for modular curve, you have the modular curve, and then you have the elliptic curves that sit over them, etc. So when you go to Hilbert modular, it's a PEL type Shimura variety. It is a quotient of a product of upper half planes, but it has a moduli space interpretation. And the fiber spaces would be abelian varieties with real multiplication by whatever the real, whatever the. So whenever you're talking about Hilbert modular stuff, you're talking about a real, a real field, right?
Right.
Totally real field.
Mm-hmm.
So you're talking about, I can tell you how one would attempt to do this, but I think it's probably already been done by some fancy French guy.
Well, if you can remember any of their names.
So I'm just saying that this is a familiar pattern. Now, I don't know that anybody's worked it out.
Right.
And what you're doing here is trying to bring it down to the realm of explicit calculations. And I think probably the thing you've written down is the correct thing. Namely, you are doing a cuspidal integral on this Hilbert modular variety. That thing is probably correct in that sense. So you're integrating over a certain, whatever the dimension of that chain is. It's not a line integral anymore. It's a but it's probably the right thing.
Mm-hmm.
So my guess is that that's what it is. But I would have to, look in the literature at this stuff. This is a familiar thing. The people who do Shimura varieties, this is second nature to them.
Mm-hmm.
Really, this is a Shimura variety. These Hilbert
Mm-hmm.
modular varieties, and it's PEL type, which means it has a good moduli interpretation, which means that you have these fiber spaces, but they're not, they're abelian varieties with real multiplications. Okay,
Mm-hmm.
that's the moduli space interpretation, and that would be the Kuga family, so to speak, that would belong to this. And somewhere in the cohomology of that Kuga variety are these Eichler periods. But I would tend to think that some guy, some gal even, I don't know, somebody over, in France or Germany or one of those places where they do this fancy stuff has already
Mm-hmm.
done it or written it down.
Yeah, I mean, wouldn't surprise me, but that is from what we've been able to read, just we haven't been able to breach like the difference in the language.
Well, part of the problem here is, and Fang-Ting and I are the same thing with our little project. Definitions can be given, but when you try and bring them down to explicit things, it's a totally different thing. You have
Mm-hmm.
to actually unwind all this fancy stuff
Mm-hmm.
to something you can calculate. That's a big deal. It's easy to write down some of these big diagrams, say, well, you have this functor, it's representable, and you have this, you have this cohomology. Well, okay, so what? But then you want to actually explicitly calculate things. That's another ball game.
Mm-hmm. Yeah, I guess when we're thinking about a more natural way to define these period polynomials, we would probably end up in H2, not H1 anymore.
Yes, exactly. No. Well, and depending on the dimension you're working with, if it's just a product of two of them,
right,
it's probably in the middle, so-called middle dimension. If you have a product of K of them. This is typically what's going to happen.
Mm-hmm.
And yeah, if you just took a product of two of them, Hilbert modular surface is probably H2. It's probably not H1. You can define these things. There's no problem in group cohomology. You just take a product. After all, these Hilbert modular groups, they have cohomology. You don't have to just take SL2Z. You can take any one of these Hilbert modular groups. They have perfectly good cohomology.
Mm-hmm.
But you're right. I think you'd be taking, it wouldn't be just be H2.
Mm-hmm.
It depends on what dimension you're in. So if it's Hilbert modular threefold, then it would be H3 probably, or something.
Yeah.
It's usually in these situations, there's one dimension that's really interesting, and all the other dimensions are sort of, I wouldn't call them trivial, but but there's one dimension you really want to know about, and that's the one that's related to modular forms.
Right. Yeah. So I believe that at least for so Ash and some of his collaborators, they've worked that out, not for Hilbert modular forms, but if you're taking automorphic forms and then you're having like SL3Z or like something like that.
Oh, absolutely. But one thing about SL3Z, I have to warn you, the symmetric space doesn't have a complex structure anymore.
Right.
So these are not algebraic varieties. So this is a really interesting problem. See, SL3Z, the symmetric space, is not Hermitian symmetric, which means you don't have a complex structure anymore.
Yeah,
you can talk about automorphic forms, you can talk about cohomology, but they don't have an obvious algebro-geometric meaning. And a lot of there are all kinds of Shimura varieties. People talk about Shimura varieties attached to unitary groups and this thing and that thing. But the Hilbert modular case is certainly an interesting one. And, I guess, it's going to be some middle dimensional cohomology group that you're going to be looking at. But I could probably look around a little bit and see, like I say, this kind of story is more or less familiar to the people who do Shimura varieties.
I see.
It's really up their alley. And
okay, well, if you ever remember any of those names, let me know. Yeah, because every time I want to look at this, it's just very overwhelming.
Of course, you see, the thing is that they're using all kinds of extremely. Just the case of Hilbert Blumenthal. This is the case of a product of two upper half planes. People like Rappaport, for example, wrote a PhD thesis on this. What are the moduli schemes that are associated to Hilbert Blumenthal surfaces? What functor do they represent? What are their compactifications? You're adding cusps, you're compactifying them. And the story of compactifications gets much more complicated, and for curves, just adding these points. When you do these compactifications in higher dimensions, you're no longer just adding points. You've got boundary components. Oh, it gets complicated and fun. Yeah, so it's a big leap, even to go up to just a Hilbert modular surface. So I don't know what. So see, there's the question here is what can people say as general things versus what can people say? I can compute this.
Right. From there to the explicit, yeah, it's a long road usually.
Yeah.
Okay. So is there any other questions or comments?
Why do you need a completed L function in your proof?
Well, let's see. If I'm going back to
well, it's that integral.
Yeah, exactly.
That's that integral. That's what comes out when you do that integral. It's right there.
So
the integral from 0 to infinity. That's a kind of Mellin transform or something like it.
Yeah, exactly. So basically,
it'll include the Archimedean factors as well.
Yeah, that's right. And the completed L function basically allows us to go from, just the definition of the pure polynomial as an integral to actually computing the coefficients.